Hello, welcome back. So we looked at the basics of probabilities. We talked about the addition law, multiplication law, and the basic definition of probability. So we will move forward and talk about mutually exclusive events. So when we say that A and B are mutually exclusive, what we really mean is that A and B do not occur together. If A occurred, then we can say that B did not occur, right? So if I were to represent this in a Venn diagram, if this is A and this is B, and we can see that there is nothing common in between them. In other words, A intersection B is 0, or even the probability of A intersection is 0, then we can say that the events are mutually exclusive. To give you an example, let's say I have two options: either I take a bicycle to school or I take the bus. If I take the bus, then it's obvious that I won't be taking the bicycle, right? So the events taking the bicycle and to school and taking the bus to school are both mutually exclusive events. So how do you check if two events are mutually exclusive or not? Well, this is basically the test, but to write out the formal test, if the probability of A or B is equal to probability of A plus the probability of B, then the events are mutually exclusive. So the general formula for probability of A or B is equal to probability of A plus probability of B minus probability of A intersection B, right? Because if you have any two circles like this, and we know that the probability of A or B is basically this whole data set, so we can say, okay, this stuff plus this stuff, and we know that what's common in between them is being counted twice, so we minus it, and so we get our formula. Now if two events are mutually exclusive, then we know that this is equal to 0, and so if this is equal to 0, we can boil it down to this, right? And previously, when I was introducing you to this addition law, I only gave you this formula because previously I gave you the example that if you have buckets and there are random few colored balls, right, and you put your hand in there and you pick one, so in it is obvious that the events of picking a green ball or a yellow ball or a blue ball are independent, because are mutually exclusive, because if I got a green ball, then it is obvious that I did not get a yellow ball or I did not get a blue ball, and so on, right? So let's look at a couple of examples. Let's say if your A, you have a couple of numbers from 1 to 10, and A is the multiples of 3, right? So in other words, A is an element of 3, 6 and 9, and let's say B has the multiples of 5, right? So B is an element of 5 and 10, right? So the probability of A or B, well, let's look at the favorable outcomes: 1, 2, 3, 4, 5. So 5 out of the 10 is the probability, so 0.5. Probability of A is 3 over 10, probability of B is 2 over 10. So we see that 0.5 is equal to 3 over 10 plus 2 over 10. We know that this equality holds. In other words, probability of A or B is the same as probability of A plus probability of B. So we know that these two events are mutually exclusive, right? And right off the bat, you could have spot out that these are mutually exclusive because there is no element that is common between these two, right? So let's look at another situation. Let's say A has even numbers and B has multiples of 5, right? And then again 1 to 10. So if A has even numbers, then A has the numbers 2, 4, 6, 8, 10, and we know 5 would be B would be an element of 5 and 10, right? So here we can see that if B occurred, then A could also have occurred because they have something in common. So the probability of A or B is, well, 1, 2, 3, 4, 5, 6. We won't count 10 again, of course, because it's the same outcome. So 6 over 10. Probability of A is 5 over 10. Probability of B is 2 over 10. we know that 6 over 10 is not equal to 5 over 10 plus 2 over 10, and hence these two events are not mutually exclusive. Right, so let's move on and talk about conditional probabilities. So let's say you have 100 people, 100 students, right? You're in a meeting with 100 students, and you ask all of them, how many of you have taken physics? Right? Let's say 50 of them raise their hands. Of course, 50 of them do not. And let's say out of the 50 students who have taken physics, 40 have taken math and 10 have not taken math. And just for the sake of completion here, let's say 30 have taken math, 20 have not taken math. Right, so you say how many of you have taken physics, right? And all of those who have taken physics, you take them to another separate room. Right, so now you're in a room with 50 physics students. You have cut off this branch, and this is now your new sample. Right, and now you are asking the question that from this sample, if I pick a random person, what is the probability that I choose a person who has taken math? So this is something that is called conditional probabilities, and this whole situation can be summed up by the notation probability of math given physics. Right, this is math given physics. So what in conditional probabilities, what we do is that, look, I have given you the knowledge that the person already has physics, right? So now your sample is reduced to the people who have physics only, and then I'm asking the question, okay, what is the probability that I now choose math? Well, if you're in this room, then you can pretty much figure out very quickly that 40 out of the 50 students have math, so the probability would be 0.8. So the general formula for conditional probabilities is probability of M intersection P over probability of P. Right, now this is the same as the formula we did here, the logic we did here, because probabilities are relative frequencies. So here, what is the probability that the person took math and the person took physics? So it's 0.5 times 0.4, and then the probability of just physics would be this would be 0.4, because 40 out of the 100 students took math, so the probability of choosing a math and given physics, choosing a math and physics is 0.4, and then choosing just a physics is 0.5, so this is also 0.8. So let's move along and look at a certain type of conditional probability that are independent events. So when we say that A and B are independent, what we really mean is that the occurrence of one event does not change the probability of the other event. In other words, these are independent in the sense that one of them does not change the likelihood of the other occurring. So let's say if it rains and the event of raining increases my likelihood of taking the bus to school, then the events of raining and taking the bus to school are not independent, because if it rains, then I'm more likely to take the bus. Right? In other words, if we take some two things that are not that connected, let's say I roll with one of my hand, I roll a die, and with the other I flip a coin. Now it doesn't matter what the outcome of the die is. The probabilities of me getting ahead will still be the same, right? So let's look at some formal definition of independent events. So A and B are independent if the probability of A intersection B is equal to probability of A multiplied with the probability of B, right? And if this is true, we can come up with two more things, that probability of A given B. So we know that this is A intersection B over probability of B, but we know that if they are independent, then this is the case, and we can cancel out these two, and this turns out to be probability of A. Similarly, probability of B given A would be probability of B. right? So when you are looking at these two, you will see that independence really means that um, the the occurrence of one event. So we know we were given that B is given. If we are given that B is given and the probability still remains the same as the probability of A, then the events are independent, right? So let's say I have this Venn diagram. There's A, there's B, right? And let's say A and B are some random events that I don't know, right? So this has 2, 4, 9. This has 7, 8, and both of them have 10 in common. And you need to check whether the events A and B are independent or not. So we know that probability of A is 4 over 1, 2, 3, 4, 5, 6. Probability of B is 3 over 6. Probability of A given B is 1 over 6. Now is 1 over 6 equal to 4 over 6 into 3 over 6? Let's see, 2 over 3, this cuts 1 over 3 is equal to 1 over 3. Now we know 1 over 6 is not equal to 1 over 3, so we can conclude that these two events are not independent. To give you another situation, let's say I'm playing a game and the probability of me winning round 1 is 0.5 and me not winning round 1 is of course 0.5. And let's say after that round 1 there's another round 2, right? And if I win round 1, then the probability of me winning round 2 is 0.5, and so this will be 0.5. But if I do not win round 1, then the probability of round 2 is 0, comes down to 0.25, and of course this would be 0.75. Now if you want to check whether the events winning round 1 and winning round 2 are independent or not, what you can check is whether R2 given R1 is equal to just the probability of winning R1, right? So if R1 and R2 are independent, then the probability of this should be the other way. The probability of R1 given R2 should be equal to the probability of R1, right? So what is the probability of R1 given R2? So we know that the event we are talking about will have this thing, will have one R2. So the denominator will basically be this path, right? So which is the probability of R2. So the probability of R2 is 0.5 times 0.5 plus 0.5 times 0.25, and we know that the favorable path that we are talking about is this one, which is 0.5 times 0.5, right? And we're asking the question, is this equal to 0.5? Now this turns out to be 2 over 3, and we know this is not equal to 0.5, right? So here you could clearly see that if I win round 1, then the probability of winning the next round increases, right? And so we can see directly that these are not independent, right? In other words, these are dependent. And that's all for today.